Welcome to CST432, Microprocessors and Embedded Systems. This is fully armed and dangerous. In this course, we will learn about embedded systems and microprocessors. Embedded systems are systems that incorporate microprocessors or microcontrollers for performing various calculations and executing tasks. Now, robots perform various tasks without close human supervision or control. Therefore, robots are examples of embedded systems. LEGO Mindstorms is an excellent platform for learning about robotics and embedded systems. There is no need for you to saw, cut, or solder any components, which can be daunting for a beginner, especially someone not from an engineering background. Secondly, the next brick is the brains of the Mindstorm robotics kit. It contains an Atmel microcontroller using the ARM7 TDMI architecture from ARM Limited. Now, this is a microprocessor or microcontroller that we'll be studying in greater detail. Of course, when we are creating robots, it involves several steps. It includes the design and the construction of the robot itself in terms of the hardware and the components that make up the robot skeleton. Now, secondly, this robotic software needs to be developed and interface with the sensors and actuators that are part of the hardware components. Finally, the robot that has been developed and built needs to be debugged and tested to see that it performs the task it's intended to do. Now, in this course, we will focus on the last three components of these steps. Now, the robotic software development, interfacing, and robot debugging and testing will be the focus in this course. Robotic software development involves writing programs that execute on the next brick. Existing programming languages and environments for the LEGO Next include the default NextG visual programming environment. This is something that comes as part of the Mindstorm kit. Alternatively, third-party firmware provides Java, such as found in LeHOS, or C, such as found in NXC, Robot C, and so on. We shall do something slightly different for this course. Instead of using the built-in default languages or even some of the available languages, we will focus on learning ARM assembly language programming using the LEGO Mindstorm kit. Now, the first question someone might ask is, why? Why do we want to learn about assembly language, or bare metal programming, as is also known as? The first reason is because you can overcome any performance war that you may encounter if you use a high-level language. Now, you may not realize NextG and Java are both virtual machine based. This means that they are being emulated on the ARM microcontroller in the Next. Secondly, the execution efficiency of programs is highly dependent on the language that is used to program the system. A high-level language may allow the user to develop a program easily, but it causes overheads in terms of the execution speed. Now, the bare metal programs, such as those written in C or ARM assembly, allows us to tap the power of the microcontroller directly because we can access the hardware and low-level components directly in our programs. Now, another reason for learning about ARM assembly language is because this is a robot is an example of a real-time embedded system. So by learning about programming in the Mindstorm, we will also learn about real-time embedded systems. This is also a good way to learn about the ARM microprocessor architecture, which is found not only in the LEGO Mindstorm, but also in other more advanced ARM systems, such as those found in smartphones and tablets, including those that are used by Android and Apple iOS. Finally, a good reason for doing it is because it is fun. Before we start on this journey, I would like to start by introducing you to a bit of history. Microprocessors has been around since the 1970s, and they have evolved over the past 40 over years from being 4-bit processors to 64-bit processors that we find and use commonly today. Now, this has caused a significant change in terms of line width, which shrunk from 10 microns down to 20 nanometers. Transistor counts, which increased from 2000 transistors in a microprocessor in the 70s to more than 1 billion today. Thirdly, the clock speeds has also grown from less than 1 megahertz to more than 3 gigahertz. It's a great increase in processing power. Unfortunately, power consumption has also increased from less than 100 milliwatts to more than 100 watts today. In this diagram, we see some history of the microprocessors that have developed over the years. This is not a complete list, but it lists some of the more popular processors. Now, we shall start with the CISC or complex instruction set computers microprocessors, including the Intel family, which started from the 4044, then it evolved into 8080, 8085, and then 8086, 8088 for 16-bit processors, and today we have the 32-bit and 64-bit variants, such as found in the Core, Core 2, and I family processors from Intel. At the same time, we also have other companies that developed 8-bit microprocessors during the golden era of microprocessors, of personal computers. The first one that is most popular is from Western Digital, which came out with the 6502, and it was found in the Apple II and other personal computers of its era. At the same time, Motorola also had some 6800 and 6809 processors, as well as the Z80 from Zilog. Now, these processors are no longer in common use today, but it defined an era in microprocessor and personal computer history. Today, most of the CISC processors are typically 32-bit in size or greater, depending on the application as well as their use. The next group of processors that we'll look at are RISC or reduced instruction set computer microprocessors. These were developed in response to the bottlenecks and the difficulties in scaling up the performance of CISC processors in the 80s. Now, in this list, there are several companies that spearheaded the development of RISC processors, including Sun Microsystems with the Spark family, the MIPS Technologies with the MIPS family of processors. IBM came up with the Power family, which was used in their workstation line, as well as evolved into the PowerPC family of processors used by the Apple Macintosh in the late 90s and beyond. And finally, Hewlett-Packard came up with the PA RISC family that was in use in their workstations. Most of these processors were developed as 32-bit processors, but some of them were also extended to become 64-bit processors. Unfortunately, most of these processors are no longer in the market today, except for perhaps those from Sun Microsystems and IBM in their mainframe and other high-end computers. So what happened? Well, we find that microprocessors actually have become embedded, meaning that they have been included into microcontrollers. Now, microcontrollers are devices that include a microprocessor core, memory such as flash or EEPROM, and RAM, in addition to other peripheral logic that is used for controlling devices, and these are all integrated into a single die for performance as well as size reduction reasons. Now, typically microcontrollers are found in many of the items we use in our daily lives, including washing machines, microwaves, TV sets, as well as personal assistants, digital assistants such as PDAs and smartphones, and even tablets. Now, in this diagram here, we see some popular CISC microcontrollers. Now, these microcontrollers are very low-end to very high-end devices, including those that are 4 bits, which are not commonly used in the computers today, but it may still be found in simple devices such as your remote control for your television set. Okay, so there are many vendors of microcontrollers, and it is too many to list in this slide, but this is just a sampling of some of the microcontrollers that have been popular and may still be in use today in many devices. As I mentioned previously, a lot of the RISC processors are no longer in the market today. Now, they have become embedded microcontrollers, and they are actually in great use or in popular use in many devices, especially those from the MIPS technology platform, are commonly found in printers, routers, and other home devices. PowerPC based devices are commonly found in automotive industry as well as other high-end applications. And as you can see here, now the ARM processor family is interesting. The ARM Limited does not actually make their own microprocessor or microcontrollers. Instead, they license it as an intellectual property block for inclusion in other vendors' microcontrollers. So we can find ARM processors in many vendors' devices, including families such as Strong Arm, Xscale, which was from Intel at one point. And today we have many vendors that provide processors based on the ARM Cortex family, as well as other FPGA vendors that incorporate the ARM core into their FPGA devices. Now, what are some of the common characteristics of microcontrollers? First, they feature what is called an all-in-one design. Okay. Secondly, their robustness, or how they can be used in specific instances. And thirdly, the low power consumption. Most microcontrollers are able to perform all their tasks with just a few additional logic circuits. This means that in any device that includes a microcontroller, you need to add a few external devices or components to make a complete system. Now, such designs reduce space requirements, power usage, and also improve reliability, because the less parts you have, the less things will break or go wrong. So currently, microprocessors have become systems on a chip. We have shrunk a PC from a desktop or even a room size down to something you can carry in your hand and runs on battery. Another important feature of microcontrollers is the robustness. Now, we can categorize devices or electronic devices into three main categories. The first one is called consumer or protected category, which are typically found in offices and indoor usage. Now, the temperature range that is expected for this device can be from 0 degrees to 70 degrees Celsius. The second category is called industrial or normal usage, which is typically used for outdoor or industrial settings, such as in factories, in difficult environments, such as in for safety and public safety and search and rescue operations. And this tends to be has to tolerate temperatures from minus 40 degrees to 85 degrees Celsius. Finally, we also have what the highest spec, which is the military spec or mil-spec devices, which are meant for severe or extreme usage environments. So for these type of devices, they are able to survive in temperatures from minus 55 to plus 125 degrees Celsius. Now, the ability of a system to overcome temperature differences, mechanical vibrations, and electrical and voltage current changes are other factors that affect the robustness of the device. Now, typically, microprocessors are built for consumer grade usage. So, in other words, if you have a normal Intel processor in a PC, you don't expect it to function well in an outdoor environment. However, microcontrollers have industrial and military grades so that they can be used in more extreme environments, and are typically needed for anything that is portable and can be carried from indoors to outdoors or used in more harsher environments. Low power consumption is critical for portable or battery operated embedded systems. We do not want our handphone or smartphone to die on us as we are in the middle of a conversation or in the afternoon during lunch. And to overcome this problem of high power consumption, we normally need to implement power saving modes. And these power saving modes will stop the execution of certain devices in the system that we are working on, so that they will not be powered when not in use. Now, processors include such things as sleep mode to lower the power consumption during idle periods. There is a deep sleep mode in most microcontrollers that can lower the power consumption down to less than 1 milliwatt. To get everyone up to speed, we will also learn about some important definitions. This may be a revision to you, but in any case, bear with us. For computers and computer systems, there are some basic definitions such as a bit, a nibble, a byte, and half word, word, or double words. A bit is the most basic unit of measurement in any computer system. is a binary digit. A nibble is actually consists of 4 bits grouped together to form a value. A byte is 8 bits or 2 nibbles. And a word, now word is more complex. It depends on the processor type that you are studying or trying to understand. An 8-bit processor will have a word size of 16 bits because a byte is already 8 bits. However, on other processors that are 16-bit or 32-bit or 64-bit, the word is typically the natural integer size of the processor. Now, the word size in a 16-bit processor is therefore 16 bits, whereas the word size in a 32-bit processor is 32 bits. Now, sizes that are greater than the natural word size of the processor are known as double words, quad words, and so on. Now, typically, these sizes are sufficient for our use today. How do we represent numbers in a computer? Computers are built on digital circuits that are binary, meaning that they have either a 1 or 0 value in the logic circuits. In order to form numbers, we will need to use what is called base 2 arithmetic. And base 2 arithmetic groups the numbers in such a way that you have a least significant bit which contains the least significant value in the number, and until the most significant bit which has the highest value bit in the number. Now, the bit significance is noted as a power of 2, which starts from 2 power 0 all the way to 2 power n minus 1, where n is the word size of the value that you are interested in. Secondly, the bit position identifies which of the bits that we are interested in. It starts from bit 0 all the way to bit n minus 1. Typically, we will assign bit 0 to least significant bit and bit n minus 1 to the most significant bit of a given number. If you are not familiar with binary numbers, this is a simple way to convert between decimal numbers, which is what we use for every day, to binary. Given a binary number such as 10110010 is also known as a base 2 number, we can convert it to a decimal number by multiplying each of the binary digit values by the bit significance of that digit. So the first one on the leftmost side of the number has significance of 7. So it is 1 multiplied by 2 power 7, add to 0 multiplied by 2 power 6, add to 1 multiplied by 2 power 5, add to 1 multiplied by 2 power 4, which forms the first 4 binary digits of the number, and then 0 multiplied by 2 power 3, 0 multiplied 2 power 2, and 1 multiplied 2 power 1, and 0 multiplied 2 power 0 is the next 4 bits of numbers that are make up our number on the screen. And this, when converted into decimal, will give us the answer 178, which is a base 10 number. To go the other way, we take the number in base 10 and divide by 2, and every time there is a remainder, this forms one of the digits of the binary number. So by dividing 178 by 2, you get 89 with a remainder of 0. Divide that by 2, you get 44 with a remainder of 1. Divide by 2, you get 22, remainder of 0. Divide by 2 again, 11, remainder 0. Divide by 2, you get 5, remainder of 1. And then 2, remainder of 1, 1, remainder of 0. And finally, 1 divided by 2 is 0, remainder 1. Now when it's written this way, we will take the value of the binary number from top to bottom as most significant bit to the least significant bit. So the number here is 10110010 in base 2. It is often unwieldy to use binary numbers when we are talking about values. Fortunately, a group of 4 binary numbers or binary digits is also a hexadecimal digit, which is also equivalent to 1 nibble. So we have a simple lookup table which you can use that lists down the values of conversion between decimal, binary, and hexadecimal numbers from 0 to 15, which corresponds to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and A, B, C, D, E, F in hexadecimal. Now that we know how to convert between binary, decimal, and hexadecimal values, we need to know how to represent numbers in positive and negative numbers in the computer. The first approach is what is called sign magnitude representation. Given a fixed number of bits, we take the most significant bit and use it as a sign bit. What the sign bit does is to indicate whether it's a positive or negative number. Typically in the computer language lingo, positive numbers have a 0 sign bit, whereas negative numbers have a 1 as a sign bit. By doing so, we will then have a number that has n-2 significant digits. Right, this part of the number is known as the magnitude, which is the actual size of the number. Sign magnitude representation works, but it's not very elegant. In mathematics, we are looking for something that is more elegant, as well as able to represent the number values in the computer in a more efficient manner. When we're using sign magnitude representation, number 0 has two different binary representation, positive 0 and negative 0. This causes a problem for the computer because this will need to detect the case where you have positive and negative 0, which are actually 0. There's no such thing as a positive or negative 0 in real life. Right? So the computer will have to detect this case. And secondly, when we're doing addition or subtraction, having sign magnitude numbers, it means that we have to have different circuits for calculating the addition of two numbers and conversely the subtraction of two numbers. In order to address this problem, an alternative approach called 2's complement has been used in computing since the beginning. 2's complement number is obtained by first performing a 1's complement, or else known as an inversion, a bit inversion of the value or the magnitude of the number. By inverting all the bits of the number, we then get the first 1's complement, and this number will add the value 1 to it to give us the 2's complement number. So 2's complement numbers remove the problem of the positive and negative 0. Secondly, it gives us one extra negative number that we can use. This is what is called higher efficiency in computing, because you don't want to waste anything if possible. So in the example of 8-bit values, we now go from plus minus 127 to minus 128 to positive 127 as the possible numbers values that we can represent using the 2's complement. Secondly, 2's complement has an interesting property in that addition and subtraction are easily performed. A subtraction of two 2's complement numbers can be performed as addition of the first number with the 2's complement of the second number. So in this example, A minus B will become A plus 2's complement of B. Finally, we need to understand what is meant by the endiness of a processor. When we're dealing with large numbers which do not fit into 8 bits or byte, we find that the processor has to somehow store it into memory in chunks. Now, most processors in use today stores data in groups of 8 bits or bytes in each memory address. So a memory address in a given processor contains space for 1 byte of information. When we have things like words and double words and quad words which needs to be stored in a memory that is greater than 1 byte in size, then we have a problem. How would we put it into memory? So in this diagram, we see a memory address map. Right? On the left, we have the address locations, which in this example starts from 1000 hex, 1001, 102, and increments linearly. Now, each memory location has space for 1 byte of data. Now, when we have a 32-bit word, which is 4 bytes in size, how do we put it into the memory locations? Well, it turns out there are two ways to solve this problem. If you are a believer in big endian approach, what you would do is that you take the most significant byte of the value and store it at the lowest address, and the next significant byte of the value into the next higher address, and so on until the least significant byte is stored at the highest address. This is also termed as a natural storage approach, because when you read the values in memory, you find that typically we will list out the memory values from left to right, from lower memory address to higher memory address, and the numbers will be displayed in the same order as the value itself. Alternatively, if you think that little endian is a better way of keeping the information, you will store the least significant byte in the lowest memory address, the next significant byte into the next memory address, and so on until the most significant byte is stored in the highest memory address. This makes sense in the way that you keep the lowest or least significant value in the lower memory address. However, it causes more problems for the programmer when you are trying to understand the content stored in memory, because the values you read will have to be reversed in order to get the actual value in memory for a multi-byte value. So we come to the end of the first lecture. In the coming lectures, we will learn about how to put together programs for make the robot do what you want it to do. Now, before we get there, we will learn about what are various computer architectures or processor architectures, algorithms, and ways of writing programming in assembly language that will enable us to do the things we want it to do. That's all.